Hello, collegiate scholars. I hope y'all are doing well today. I'm actually making this video a couple weeks before school starts, so I'm looking forward to seeing y'all soon. Also, that's why my hair and my beard are a little shaggy, but I'll be getting a haircut soon enough and I'll be looking snazzy. But today we're going to kick off Algebra 2 by talking about functions. We are going to talk about the definition of a function, what makes a function, and we're going to talk about evaluating functions from an equation and from a graph. A lot of it should seem pretty familiar from Algebra 1, but let's go ahead and jump right in. So we'll start off by comparing functions and relations. Alright, so we'll start this off with a hypothetical question. Which of these tables could realistically describe how many points Ja Morant, this guy right here, playing for my favorite team, but how many points Ja has scored at the end of each quarter during an NBA game? Explain your reasoning. So I want you to look at these tables and see which one could actually represent how he's scored over the course of an NBA game, and explain your reasoning as you answer the Edpuzzle question, starting now. Let's look at table 1. You see that after quarter 1, he has 8 points. After quarter 2, second quarter, he has 18 points. After third quarter, he has 30 points. After the fourth quarter, he has 42 points. Okay, this is a pretty good game. So that I see no problems with table 1. Table 2, however, look at the first quarter. He has 7 points at the end of the first quarter, but this also says he has 13 points at the end of the first quarter. That does not seem possible. How could he have 7 points, but also 13 points? So that does not seem to make much sense. So really, we could go ahead and throw out table 2. Let's just keep looking at it for a second. At the end of the second quarter, he has 15 points. After the end of the third quarter, we see the same issue we had with the first quarter. It says he has 27 and 29 points. So at the end of the third quarter, 27 points and 29? That doesn't make sense. How can that work? It can't. And then at the end of the fourth quarter, he has 38. So table 2 does not seem to make much sense because he can't have two different point values at the end of a quarter. He can only have one. So table 1, we'll talk about in a second here, is a function, while table 2 is not a function, it is merely a relation. So let's talk about those definitions here now. Alright, so let's compare a relation and a function. So a relation is any pair of input values, which are the x values, with output values, which are the y values. Okay, so input is x, output is y. For a relation to be a function, there must be only one output for every input. Repeat that, only one output for every input. I want you to think of another way to phrase that and answer the Edpuzzle. Another way to phrase that is that for each input, there is only one output. So a function is always a relation, but a relation may not necessarily be a function if it does not meet that rule. Okay, so let's make sense of that by looking at these two relations. Relation number 1 is a function. All right, so the input values are 0, 1, and 2 because they are in the x value. So 0 has an output, a y value of 1. The input 1 has an output value of 2, and the input 2 has an output value of 4. Relation number 2 is not a function. 0 has an output of 1, but we see that the input 1 has 2 different output values. Okay, so that is not a function. There must only be one output for every input, and that is not the case right here with the input 1. It has 2 outputs. Alright, so let's play a quick game I like to call function or nah. Let's look at this table. So we have our x values, the input values, 4, 2, 0, -2, and -4, and then we have our output values, the y values. Alright, so the output value for the input 4 is 2. For the input 2, the output is 2. For input 0, output is 0. For the input -2, we have -2. For -4, we have -4. Alright, so all these input values have exactly one output value, okay? So this is a function. So you may say, Mr. Bender, we see 2 twice. That is, 2 is an output value twice. Well, 4 has only one output value. It's 2. The input value 2 has an output value, which is also 2. But 4 and 2, they each just have one output value. So based on our definition of a function, each input has only one output. This still works. It still fits that definition. So this is a function. All right, so our next table, let's think. Is it a function or not? Well, for the input value 4, we have one output value 4. For the input value 2, we have 2. For 0, we have 0. For 2, we have negative 2. All right. And for the input value 4, we have an output value of negative 2. Well, what do you notice here? I see that the input 2 is listed twice with 2 different outputs. So the input value 2 has an output of 2, but also of negative 2. So that input cannot have more than one output. So this does not fit the definition of function. We will say, nah, fam, not a function. Let's move on. So let's determine if this one is a function or not. All right, so we see the input values, the x values, 4. 4 has an output of 0, and it has an output of 4. That's not going to work. Let's go ahead and say, nah, fam, this is not a function. All right, how about this graph? We have a different representation of a function here. Well, so the x values, like we've been saying, are the input values. The y values are the output. So for the x value of 0, the y value is also 0. For the input of 1, we see a problem. The y value is negative 1, but it's also positive 1. So for this input value 1, it has an output of 1 and negative 1. It can't have 2 outputs. It can only have one output. So therefore, it's not a function, right? It's just a relation. So here's a tool that you may be familiar with that can help us determine if a graph represents a function or if it's simply a relation. So if a graph represents a function, then you can draw a vertical line anywhere through that graph. It would only pass through one point. Now you see over here on the right side, this is just a relation. It's not a function. You see that vertical line passing through more than 1 point. In fact, it's passing through 3 points. But even if it just passed through 2 points, it is not a function. So let's practice using the vertical line test. All right, let's look at these points on this graph. And let's just practice drawing a vertical line. I'm going to draw a vertical line through each of these points. Each of these vertical lines that's passing through one of these points, that's the only point they're passing through each time. So because they're only passing through 1 point, they pass the vertical line test. This is a function. Eyeball this one. Can you see anywhere that it wouldn't pass the vertical line test? What input value would it not pass the vertical line test at? Oh, I see. At the input of 1, we can draw a vertical line right here, and that vertical line passes through 2 points, okay? Now, you don't have to draw a vertical line. You may be able to just visualize. This circle clearly does not pass the vertical line test. I can draw a vertical line through here. Again, pretend it's vertical line through here, wherever I draw it on this circle, except for maybe right here on the side of the circle. I can draw a vertical line through the circle, and it'll pass through 2 points. So this definitely does not represent a function. And again here, you see that this is definitely a function. We can draw a vertical line anywhere through those points, and it will only go through one single point. So this represents a function. Now let's talk about function notation. When a function is written in function notation, it looks like an equation, but instead of y, you have f of x. So here are a couple of examples. Here's an equation, f of x equals 2x squared plus x minus 1. And then here's an equation where we are substituting 3 into f of x. Everywhere you see the x, we're just substituting in 3 and evaluating. F of 3 here, when we substitute 3 into this equation, I'm going to take this a step further. So f of 3 equals, so 3 squared is 9, so 2 times 9 is 18. Remember, we do the exponents first, order of operations, plus 3 minus 1. So 18 plus 3 is 21. 21 minus 1 is 20. So f of 3 equals 20. Function notation helps us to evaluate the function. F of 3, when we substitute 3 into that equation, it equals 20. So the y value, the output, is 20 when the input, the x value, is 3. So let's try these together. What we're going to do is substitute 2 into the function. Because it's f of 2, we're substituting in 2 for x. Okay, so we'll say f of 2 equals 7 minus 2, and I'm going to substitute 2 in for x. Anywhere I see an x, I'm going to substitute 2. f of 2 equals 7 minus 2 times 2, which is 4. So f of 2 is 3. Now, let's run through these really quick. We could probably do the rest of these in our heads. So f of 0, that just means we're substituting 0 into x. Well, 7 minus 2 times 0, 2 times 0 is 0, so 7 minus 0 equals 7. All right, so now for f of negative 3, we're just going to substitute negative 3 in for x, so 7 minus 2 times negative 3 is going to give us 7 minus 2 times negative 3. Negative 2 times negative 3, that's going to give us positive 6, so we're going to end up saying 7 plus 6, which is going to equal 13. So f of negative 3 equals 13. Now try these on your own. h of 3, I'm substituting 3 in here. So I'm just going to work this below here. So 3 squared minus 3 times 3 plus 2. 3 squared is 9 minus 3 times 3 is 9 plus 2. These will cancel out. So h of 3, I'll write this up here. h of 3 equals 2. We're just left with 2. h of 0. Well, we can substitute 0 in here pretty easily. 0 squared is 0 minus 3 times 0. Well, both of those are just going to be 0. So 0 minus 0 plus 2. h of 0 is also 2. h of negative 1. Substitute that in there. So negative 1 squared minus 3 times negative 1 plus 2. Negative 1 squared. Negative 1 times negative 1 is just positive 1. So negative 3 times negative 1 is plus 3 plus 2. So that equals 6. h of negative 1 equals 6. All right, so let's wrap this baby up by finishing out with evaluating functions from a graph. Here are a couple examples that you can look at on the slides that I've uploaded to Google Classroom. All these slides are on there if you need to look at them. Let's go ahead and move forward and work some problems together. All right, so we're going to evaluate this function, the graph of this function, for f of 2, f of 0, and f of negative. For number 1, it's saying that the x value is 2. So what I'm going to do first is I'm going to look at the x value of 2. So here's the input value of 2. Now what's the output value at 2? So I'm going to go up to find the y value. So x value is 2. The y value is also 2. So when x is 2, y is 2. So f of 2 equals 2. I'll do the same thing for f of 0. I'm going to look at 0 on the x-axis, so right here, and then I'm finding the y value on that graph. So going up to the graph, oh, and the y value, when x is 0, the y value is 4. Doing the same thing for f of negative 3. So finding negative 3 on the graph, so here's negative 1, negative 2, negative 3. Going up to the graph, well, the y value, the output value, is 1. So when x is negative 3, when the input is negative 3, the y value or the output is 1. So try these on your own and answer them with the ed puzzle. So for f of negative 2, saying the x value, the input value is negative 2, and then we're trying to find the y value or the output value. I'm going to go straight down until it hits the graph, and it looks like it hits that graph at negative 6. All right, not quite at negative 5. Keep going, negative 6. So f of negative 2 is negative 6. f of 0, all right, so 0 on the x-axis, and it looks like it hits the graph at negative 1 when y is negative 1. So when x is 0, when the input is 0, y value is negative 1. The output is negative 1. f of 5, x value is 5, y value is 4. When x is 5, y is 4. We could also write these as coordinate points too. The x value is negative 2, right? Negative 6, so that's for number 1. This would be 0, negative 1, and these would be 5, 4. Okay, so there you see it in ordered pair form, you see them on the graph, you see it in function notation form as well. I hope this video was helpful and was a good review for you. If you have any questions or struggling, I suggest that you look through the slides or you replay the video or parts of the video. And if you still have any questions, have those ready for me when we get to class. Okay? So great job. Thank you, collegiate scholars.